All right, section 1 is about taking apart numbers and shapes and writing equivalent expressions using the distributive property. Learning goals in this very first section lesson is to write, read, and evaluate equivalent numeric expressions. Identify the adjacent side lengths of a rectangle as factors of the area value. Identify parts of an expression, such as the product and the factors. Write equivalent numeric expressions for the area of a rectangle by decomposing one side length into the sum of two numbers. And apply the properties of operations, such as the distributive property, to rewrite the product of two factors. Key terms that we are looking at here include numeric expression, equation, and the distributive property. Down below kind of goes through what we have done before and what we are going to be doing in the future. You have learned how to operate with numbers using different strategies. Sometimes taking apart numbers before you operate can highlight important information or make calculations easier. How can you use these strategies to express number sentences in different ways? Okay. Calculate the area of each rectangle, show your work. And as we were starting, we knew that the area of a rectangle is length times width or base times height. In this particular example here, we would have, 15 times 6. And if we do have 15 times 6, then we would get an area of 90 inches squared. For this second one, it's also a rectangle. I would also have area is base times height. For this one, I would put in 12 times 9. And after I put in 12 times 9, I would get as my answer 108 yards squared. And so that is the other part of the warm-up. So when I'm finding the area of a rectangle, I would take base times height. Getting started. Form of 24. Consider the number 24. What comes to mind? 1. Write 5 different numeric expressions for the number 24. We had the class do this, and we had a whole bunch of different solutions. Some involved adding. Some involved multiplication. Some involved subtracting. Some even involved division. Some had equal signs. Some were just expressions. So, in mathematics, a group of symbols that make a mathematical statement is called an expression. A numeric expression is a mathematical phrase that contains numbers and operations. In some of our warm-ups to start the year, we talked about how these are all expressions because they don't have an equal sign, so it's a phrase. And this one is an equation because it is a sentence and it has an equal sign. We shared our numerical expressions with our classmates. Did you and your classmates use common strategies to write your expressions? Explain. And I would say that yes, we all used numbers and operation signs. Next, how many possible numeric expressions could you write for this number? And I would say that there are an infinite number of expressions. for 24, or any number for that matter. So, for instance, we never really talked about the idea that we could use more than just two numbers. Most of our expressions were just two numbers, but we could use something like that, where we could use a whole bunch of numbers to equal 24. Okay. What you notice about the collected set of numeric expressions representing 24? Well, except for the one that was an equation that was wrong, they don't have any equal signs. Something I would notice is they all used operation symbols. And so that's like addition, subtraction, multiplication, division. If I was to take a look at this as well, I could say that if I evaluated them, they would equal 24. Okay. And those are some noticings. There could be more. All right, we're on activity 1.1, connecting area models and the distributed property. Consider the equation 5 times 27 equals 135. An area model to represent the product of 5 and 27 is shown. The area is 135 square units. On the right-hand side here, we have some vocabulary. An equation is a mathematical sentence that uses an equation equal sign to show that two or more quantities are the same as one another. Remember that an area model is a rectangular array of identical rows and identical columns. Draw a line to split one side length of the area model into two parts to represent the area of 135 square units a different way. Label the dimensions of the smaller regions in the area model. And so we showed splitting this area model up like this in class. And we showed how this side would be 20 and this part of it would be 7. And then inside of here, we had 5 times 20 would be, there's 100 squares in this part, and 5 times 7 is 35. There'd be 35 in this part. Okay? And so I did this above. And so this is a different way for us to show 27 times 5, breaking down the 27 into two parts of 20 and 7. Calculate the area of each of the two smaller regions. Okay, and so I did that. It's 100, and then it's 35. How does the sum of the two smaller regions compare to the total area of 135 square units? So originally they showed you that 5 times 27 is equal to 135. And this question is saying if I take those two sums together, well, 5 times 20 was 100, and 5 times 7 is 35. And when I add those up, I get 135. And so how does the original total compare to this total? They are the same. Or if I'm being fancy, equivalent. Don't forget to use parentheses to group numbers. Okay, so I could think of this a different way. Rewrite the original equation 5 times 27 equals 135 with an equivalent equation to represent the model you drew. How can you rewrite the original product by substituting the sum of the two lengths making up the split side? Well, if I was to take 5 times 20 plus 7, that would be an equivalent, that would be an equivalent way to show that. I could say that this equals 5 times 27, because that would be the next line down. I remember to use parentheses because she mentioned it. Don't forget to use parentheses to group numbers. And I wanted to add those first, so I put parentheses around those first. All of this is stuff that we did in the warm-ups or in the little lesson that we were writing on the board as we were going. All right, so now we're continuing with that example. And so the first thing they ask, and notice how it's a B, so that's a continuation from the last question that they asked you. How can you rewrite the total area as the sum of the areas of the two smaller regions? Well, on the last page, we had 5 times 20 plus 7. Well, I could rewrite that as the sum of the areas of the two smaller regions as taking 5 times 20, because I multiplied those two together to get the 100, and then I added to that the 5 times 7 to get the other part. Think about other ways you could split one of the factors and write a corresponding equation. What would the equation look like if you split one of the factors into more than two regions? Mark and label at least 2 more ways you could divide the area model. Write the corresponding equations. Then verify that the sum of the smaller regions is equal to 135. Okay. So we talked about, and we did this in class actually, that we could say that this is 5, and then in this section right here, we could have done a whole bunch of things. We could have went halfway down and could have made one part 13 and the other part 14, and then that would add together to be 27. We also talked about having one part being 17 and one part being 10, and then we add those together and we would also have 27. If we're filling this in, 13 times 5 would be 65, and 5 times 14 would be 70, and 5 times 17 would be 85, and 5 times 10 would be 50. And you could have done a whole bunch of different ways to do this, but I just chose 2. We put several of these, I believe we put 4 on the board, 4 different options on the board for you guys to choose from for this. Reflect on the different ways you can rewrite the product of 5 and 27. Select one of your area models to complete the example. So I'm going to choose this one to complete the example. 5 times 27 would be the same or equivalent to 5 times the quantity of 13 plus 14, because 13 plus 14 is 27. Then, instead of adding those together first, I could think about taking 5 times 13 and then adding to that whatever I got for 5 times 14. And then in the next row down, 5 times 13 was 65, 5 times 14 was 70, and when I add those two together, I still get 135. So even though I'm breaking up 27 in different ways, like 20 and 7 in our first example, in our second example that I showed, I broke it up to 13 and 14. And even if we did 17 and 10, whenever we add our two products together or our different products together, we always get 135. No matter how we break up 27, as long as we multiply all the parts by the other factor of 5, when we add it all together, we get 135 at the end. Okay, So when we were doing that, we just used the distributive property. The distributive property of multiplication over addition states that for any numbers a, b, and c, a times the quantity of b plus c is the same as taking a times b plus a times c. All right? So explain the distributive property using the area model shown. Well, I could figure out the area of that rectangle by taking a, the height, and multiplying it times b plus c to get the length or the base. Or I could do each part. I could take a times b and then add to that a times c. Okay, so if I'm thinking about this, is I could either add the lengths together and then multiply by the height, like the left side of the equation. And so that's over here. Or I could find the area of a times b and then add it to the area of a times c. Okay, so either I could add these two together and multiply it by a to get the area of the whole rectangle, or I can find the area of this rectangle by taking a times b and then add it to this rectangle, which is a times c. Okay, and so the pen part is that, and then the pink is that. You can also use grouping symbols to show that you need to multiply each set of factors before you add them. And we've been talking about this, how I can put parentheses around, and that means that I'm multiplying things together. Okay. Worked example, an example of the distributive property. So this is with variables, which can be a little confusing at first, this top part. And this would be with numbers, kind of like what we did with the original example of 5 times 20 plus 7 being the same as 5 times 20 plus 5 times 7. So here, I could either do this where I add the two parts together first, and I'd have 17 times 4. Or I can multiply 4 by the parts like they showed here. I take 4 times 2 and write that first for this part. And then I take 4 times 15 and I add those two together. There's different ways to read this There's different ways to read the expression. You can read and describe the expression 4 times the quantity of 2 plus 15 in different ways. For example, you can say 4 times the quantity of 2 plus 15. So that's kind of how I said it originally. 4 times the sum of 2 and 15, or the product of 4 and the sum of 2 and 15. You can describe the expression 4 times the quantity of 2 and 15 as a product of two factors. The quantity 2 plus 15 is both a single factor and a sum of two terms. Now, this is confusing stuff, which is why it's important for us to kind of read through it. Right here, these three things are ways that we can say this. And they're just trying to say there's two main parts here. There's the 4 is one part of, and when they use the word factor, they're talking about multiplication. So 4 is one of the factors, and then 2 and 15 is the other factor. Okay? Write an equation in the form A times the quantity of B plus C equals A times B plus A times C for the other area models you created in this activity. Well, I could do this for all of them, so let me see here. First, and I have this one up here, but I could write it here, 5 times the quantity of 20 plus 7 equals 5 times 20, and I could write that a couple different ways, plus 5 times 7. Or if I think about it, the first one I showed was, or the next one I showed was 5 times the quantity of 13 plus 14. And I could rewrite that as 5 times 13 plus 5 times 14. And then there was the second one that I didn't show all the way. 5 times the quantity of 17 plus 10. I could rewrite that using the distributive property as 5 times 17 plus 5 times 10. All right, and so that would be the other area models I've created in this activity, and I'm using the distributive property to rewrite it. This side is equal to this side, it's just a different way of writing it. The properties change the order of operations, but they don't change the answer. Activity 1.2. Interpreting a real-world situation using the distributive property. Tyler is setting up the gym floor for an after-school program. He wants to include a rectangular area for playing volleyball and another for dodgeball. He also wants to have an area for kids who like to play board games or just sit and read. So the gym floor, the gym floor would be like this, and he says, I like to draw pictures as I go to kind of help me out. It would be 50 feet by 84 feet, or 4,200 square feet. Square feet. Okay. And if I was to take a look at this, if I took 50 times 84, I would get 4,200 square feet. Okay. Create a diagram to show how you would split up the gym floor. Represent your diagram using the distributive property and write an explanation for the areas assigned to each activity. Okay. So I would want to have it so we have our gym, and the after school program has to have an area for playing volleyball and another for dodgeball. He also wants to have an area for kids who like to play board games or just sit and read. Okay, so I'm going to keep this like this. And then I would think back to a lot of gyms that I have. I would probably want to make it so this is maybe I do 20, and you could choose whatever you want. And then maybe I would do, let's see here, um, 64, and then I could do maybe 32 and 32. Okay. That way, let's say I would have, let's see here, this would be 1,600 square feet. This would be the same thing, 1,600 square feet. And then this one would be 1,000 square feet. Okay. And so for me, I would have it be where those two are going to be volleyball and dodgeball. because they need a lot of room. And then this would be reading or board games because they don't need quite as much room. Okay, you could split it up a whole bunch of different ways. It says to represent your diagram using the distributor property, and I would write further the explanation for the areas assigned here. I would say how I would need more room to play volleyball or dodgeball. I would say how I wouldn't need quite as much to read or play board games. The distributor property will look something like this. I would take 50 times 32 plus 32 plus 20. And that would be equal to taking 50 times 32 plus 50 times 32. Oh, I hate that. Sometimes you run out of room here, and I'm going to rewrite this whole thing down below. So I could take 50 times the quantity of 32 plus 32 plus 20, and that could be equal to 50 times 32 plus 50 times 32 for the dodgeball plus 50 times 20 for the board games. Okay. If I add these all together, it'd be 50 times 84, which is 4,200 feet. For this one, it would be 1,600 square feet. So if I add that together, 1,600 square feet plus 1,600 square feet plus 1,000 square feet, I get a total of 4,200 square feet. So my answer stays the same. I'm just splitting up how I'm doing this. Talk the talk. Recognizing the distributive property. Identify each statement as true or false. If the statement is false, show how you would rewrite it to make it a true statement. So we start with this problem right here, and then we go to this one right here. When I look at this, all they're doing really is moving the parentheses. So I believe that this one is going to be false. What I would do is I would have to have 3 times 2. So I start with the quantity of 3 times the quantity of 2 plus 4. And then that's going to be 3 times 2. And then I would add to that 3 times 4. 2 plus 4 is 6. 6 times 3 is 18. 3 times 2 is 6. 3 times 4 is 12. 6 plus 12 is also 18. So I know both sides are equal, and so I'm on the right track for the distributor property. For this one, 6 times 10 plus 6 times 5, 6 times 10 plus 6 times 5. This one is correct. This one, oh, they moved the multiplication sign and the addition sign. They switched them around and they took away the parentheses. So this one is false. I would start with 7 times the quantity of 20 plus 8. And that's going to equal 7 times 20 plus 7 times 8. Number 4. 4 times 5 plus 4 times 10. They multiplied the first two together, but then not the second two. So this is going to be false as well. So when I have the quantity 4 times the quantity of 5 plus 10, and I can think about it like this. If I took 5 plus 10, that's 15. 15 times 4 is going to be 60. When I take 20 plus 10, that's just 30. So those two sides are not equal, so I know it's false. Same here. 20 plus 8 is 28. 28 times 7 is going to be something. 28 times 7 is going to be 196. Over on this side, this would be 160 plus 7, so it would be 167. So they're not equal. Okay? This side would equal 196. This side would equal 167. If I follow this side would be 30. This side would be equal to 60, so I know that it's not right. For this side, it would be 15 times 6, which is going to be 90. On this side, it's going to be 60 plus 30, which is also 90. So both sides are equivalent, and that helps me show that it's true. For this first one here, This side would be 6 times 3, which is going to 6 times 3, which is going to be 18. This side is going to be 6. Side's going to be 10, so I know it's also not true. And so since they're not equal, I know they haven't used the distributive property correctly. This last one has 2 times 6, which is 12, plus 2 times 11, which is 22. This one's a tricky one. I would almost say true here, but I would show it a little differently. So I would have 2 times the quantity of 6 plus 11. Over here, I would show 2 times 6 plus 2 times 11. And so they kind of skipped a step. So on both sides, the next step would be 12 plus 22. And then after that, 12 plus 22 is going to be 34. If I did the same thing on the left side, I'll get the same answer. 2 times 17, and 2 times 17 is 34. And so I still get the same answer on both sides. This one's kind of in between. I would almost kind of say false because they skipped a step. All right, whereas the other ones weren't equivalent on both sides. This last one, they kind of skipped a step for what they would show to show the distributive property. Okay.